All right, today we're going to do something really cool. We're going to decode the blueprint of our planet. And we're going to do it by learning to read the very language scientists use to describe the Earth itself. No, really, just stop and think about that for a second. The sheer scale of it all. I mean, all the oceans, the continents, the molten core, the atmosphere. Where would you even begin to write that down in a way that actually makes sense?
You'd probably end up with something that looks a little like this. And to most of us, this looks like a chaotic mess, right? A jumble of Greek letters and symbols. It's intimidating, almost like you're trying to read some kind of secret code. And this isn't made up. This is straight out of the appendix of a geophysics textbook.
But here's the secret, the really amazing part. This isn't just some random list of variables. It's a language. Every single one of those symbols is like a word, a concept that lets scientists build a complete mathematical picture of our world. So, to understand any language, you've got to start with the basics. So that's what we're going to do. We're going to deconstruct this code by learning how to read a single word. Let's start with one that might look a little familiar, the simple letter G. In the language of Earth science, this tiny symbol represents a concept that has a massive amount of weight, literally. G stands for the acceleration of gravity. And what's so powerful about this is how it connects an abstract symbol on a page to something we all feel every single moment of every day, that force that keeps our feet planted firmly on the ground. And in this language, see, it's not enough to just name a concept. You have to measure it with precision. Gravity is measured in meters per second squared. That rigor, that exactness, is what makes this language so incredibly powerful. Okay, so we can read a word. Now let's try to build a sentence. We're going to use this new language of ours to actually construct a model of the Earth, starting with the absolute basics. Let's put ourselves in the shoes of a planetary architect for a minute. If you were building a planet totally from scratch, what are the first, most fundamental things you would need to define? Well, you'd start right here with the foundation. The symbol A gives us its size, that's the radius. M gives us its mass, how heavy it is. The Greek letter rho, or rho, tells us its density, how much stuff is packed inside. And of course, G defines its gravitational pull. These are like the structural beams of planet Earth. And just like that, with only 4 symbols, we've created the first draft of our planet. Okay, so it's a giant, static, solid sphere just kind of hanging out in space. A little boring, maybe, but hey, it's a start.
Right, but we all know the Earth isn't just a cold, dead rock. It's a dynamic, living world. So the next big question is, what's the engine that powers all that activity?
The answer is heat. The language for Earth's thermal engine starts with T for temperature. H is all the heat being generated deep inside the Earth. Q is the flow of that heat. And that Greek letter, kappa, that describes how quickly heat can move through solid rock. And to measure just how efficiently this whole engine runs, scientists use a single value called the Nusselts number, or Nu. You can think of it like a performance rating, kind of telling us how effectively all that heat is transported from the core up to the surface. And believe me, the effects of that are massive. Because this is where we see the real-world power of that engine. We're not just talking about abstract values here. This thermal engine is the driving force behind volcanoes, earthquakes, mountain ranges, and even the slow, relentless drift of the continents themselves. So that leads to a pretty huge question. How does this language describe something as massive and as incredibly slow as the dance of the continents? Well, it actually boils down to a surprisingly simple 3-step process. First, you need a force, something pushing or pulling on the mantle. That's stress, represented by the Greek letter tau, or tau. Second, you measure how the rock actually deforms under that stress. That's the strain rate, epsilon. And third, you have to account for the rock's resistance to flowing, its viscosity, which is mu, or mu. So just imagine, deep inside our planet, there's this constant slow-motion interplay happening between stress, strain, and viscosity. And it's that very process, described by just these 3 symbols, that is powerful enough to move entire continents across the face of the Earth over millions of years. It's just incredible. But like any rich language, this one has its nuances. It's got complexities. Remember our very first symbol, A? We learned it as the radius of the Earth.
But depending on the specific problem a scientist is working on, it can also mean the radius of just the mantle, or a proportionality factor, or a whole bunch of other specific things.
Now, that's not a flaw, it's a feature. It shows you how flexible this language is. Scientists adapt their vocabulary for the very specific problem they are trying to solve, whether they're modeling the whole planet or just one tiny piece of it. It's all about precision.
So, as we bring this all together, what does this journey through the symbolic language of Earth science really show us? Well, it shows us a whole new way of seeing the world.
It reveals that these aren't just symbols, they are the actual tools scientists use to build a functional, mathematical model of our planet. We see how that model is built in layers, from a simple static rock to a dynamic engine to a world in constant motion. Every symbol is a critical piece of this single, vast, interconnected puzzle. This is the blueprint that helps us read our planet's history and maybe even predict its future. And maybe the most inspiring part is that this work is never really done. The language is still evolving as we learn more. Every symbol really does represent a piece of a grand, interconnected puzzle that scientists are still solving right now, today. Which leaves us with a final thought to chew on. If these symbols really do form the language of our planet, a language that tells the story of its creation and its entire life, what incredible stories are we still just learning how to read?